Good morning, children. Today we are discussing about real number and sets. Important concepts we can try to cover. First of all, real number. What is the introduction? Here, real number. First, if you know counting numbers, those are the natural numbers 1, 2, 3, and sets we can write in the braces, and dash means that is the infinite set, uncountable. And after this 1 to 3, those natural numbers we are adding to 0, then it becomes a whole number. And if this whole number, if you add negative numbers, then it becomes an integer set, minus 1, minus 2, minus 3, dash, and 0, 1, 2, 3, dash. And if you the numbers not only in the form of integers, they can be in the decimal form or p by q form. Then bigger than this set is rational numbers, that is we can write as in the form of p by q. The denominator is not equal to 0, and p comma q are integers, and p comma q are co-primes. This rational number in the form of two types. One is terminating decimal form, and other is non-terminating recurring decimal form. Repeating, block is repeating. And if you go irrational number, that is p by q, and those are irrational number cannot be represented in the form of p by q. Why? Because rational and irrational are different, and those root 2, root 3, those are non-terminating, non-recurring. That's why we can call as those are irrational numbers. And pi, and here the 1.14, 10, 100, 100, like this. Here the block is not repeating. 10, 100, 000, like that you are getting. That's why this is a non-terminating, non-recurring. That's why we can call as those are irrational number. And real number is nothing but union of rational and irrational. We can represent sets like this. Natural number, and natural number is subset to whole number is subset to integer, and integer is a subset to rational, and irrational number is separate set, and this is a real number set. If any element is in this whole number, then that is also in the real number, because this is the bigger set. But if the number element in the real number, we cannot say that is in the integer. That may be in the irrational also, or we can say rational, anywhere it stays. And the major topics here we need to cover in this real numbers is, first concept is Euclid's division lemma, and second one is fundamental theorem of arithmetic, and the next one is prime factorizations, and HCF and LCM, small 1 or 2 marks questions they can ask. And here Euclid's division lemma we can expect from HCF is 1 mark, or Euclid's division lemma problems they can ask 2 marks or 4 marks. And composite number, based on that concept they can ask. Terminating decimal form we already studied. Terminating decimal form means converting p by q into decimal form, decimal into p by q. And if non-terminating recurring means we can write as a again we can convert into p by q, that is periodicity based on that. And root irrational problems, very important, this one or this one, chances to get 4 marks. Euclid's division lemma or root irrationals. And the last concept is logarithms. If you go for the first concept, Euclid's division lemma, finding the HCF of two numbers. Here this they can ask 1 mark question. HCF of any two numbers, if you take 3 and 17, or choose any 2-digit number, your wish, but I am selecting 3 and 17. First of all, we need to division with this method: 3, 17, dividend and divisor, quotient and remainder. But we need to continue, remainder should be 0 until. How can we do? Means 3 goes 5 times is 15, the remainder is 2. Again this becomes the divisor, and this divisor becomes dividend. 2 1s are 2, and remainder is 1. And again this divisor is dividend. 1 2s are 2, remainder is 0. Whenever the remainder is 0, the divisor itself is a HCF, and we can write as algorithm means, here we can write as 17 is greater than 3, we can write 17 equal to 3 into divisor equal to dividend equal to divisor into quotient plus remainder, we can write. Then the next step is again dividend equal to divisor into quotient plus remainder, and again dividend equal to divisor into quotient plus remainder. Finally, whenever we got a 0 remainder, then the divisor is a HCF. We can conclude from here HCF is 3, 17 is 1. always if the first step only we can get the remainder is 0 means the divisor itself is a HCF. And if you go in this model, they can ask 1 mark, 2 marks. 1 mark means they can ask the chances is HCF of two numbers, and if they can ask even integer in the form of 2q, odd integer in the form of 2q plus 1, they can ask those model 1 mark or 2 marks. And every odd integer in the form of 4q plus 1, 4q plus 3, we need to show that this every odd integer. And textbook model 1 is 6q plus 1, 6q plus 3 or 6q plus 5. We need to show that every odd integer in the form of 6q plus 1, 6q plus 3 or 6q plus 5 by using equivalence division algorithm. First thing we need to define the definition. What is equivalence division lemma? For any two integers, if you take, there exists quotient and remainder. This process will be unique. If you take 2, 7, 2 3 is 6 and the remainder is 1. For these two integers 2 and 7, one is dividend and other is divisor, then you will get exist quotient and remainder. That is a unique integers will exist. Then in the same way we will use the definition by Euclid's division lemma. For any two positive integers a and b, there exist q and r, such that we can write the condition is dividend a equal to divisor into quotient plus remainder. Here the remainder is 0 or sometime greater than 0, but always less than the divisor. 0 less than or equal to r less than b. And here we need to compare in the question 6q. 6q means here we take as b as 6, then the remainder is chances 0, 1, 2, 3, 4, 5. Then we can substitute the values here. In the place of b is 6, in the place of remainder we are changing 6q plus 0 or 6q plus 1, 6q plus 2, 6q plus 3 up to 6q plus 4 or 6q plus 5. Now we need to check each number. Here if you take first number 6q we can write as 2 into 3q. 2 multiple is always even integer. That's why we can conclude that 6q is an even integer. If you add 1 to the even integer, then it becomes odd integer. Then 6q plus 2 or 6q plus 4 are the even integers. Then we can say that 6q plus 1, 6q plus 3 or 6q plus 5 are odd integers. Therefore we can conclude that again we need to write in the finally therefore, and we repeat the question again. Every odd integer in the form of 6q plus 1 or 6q plus 3 and 6q plus 5. Next we can discuss with same model, but they can ask the question square of the number in this form by Euclid's division lemma, cube of the number in this form. The second model is here by Euclid's division lemma, square of any positive integer in the form of 3p plus 1. For this again we need to go same way. By definition, for any two positive integers a and b, there exist q and r, such that a equal to bq plus r. And the condition is remainder should be 0 less than or equal to r less than b. Remainder should be greater than 0 or equal to 0, but always less than the divisor. And here when we compare here 3p plus 1, we need to show that in the form of, then here we will take as b value is 3, then the remainder is 0, 1, 2. Then substitute this b and r in the a integer, a equal to 3q plus 0 or 3q plus 1 or 3q plus 2. Then a equal to 3q. Now this number in the question they given square of the number. We need to squaring on both sides. Then this formula we can apply ab whole power m, a power m, b power m. A square equal to 3q whole square, that is 9q square. 9 we can write as 3 of 3q square, nothing but 3p. The square of the number in the form of 3p. If you take second number, this first number we done square. Take the second number, again squaring on both sides. You will get a plus b whole square. Here a square plus 2ab plus b square. Then we can write 3q whole square is 9q square. 2 into 3q into 1 is 6q. 1 square is 1. Then we can, first two terms we can take common as 3. Then we can write 3 into 3q plus 3 into 3q square plus 2q plus 1. Then we can write this is in the form of this one total thing we take as p. Then we can write a square equal to 3p plus 1. Most of them will stop here only. Why? Because they think that 3p and 3p plus 1, the square of the number. But here we are having 3 numbers. 3q plus 2, that number also we need to square. A equal to 3q plus 2, squaring on both sides, then we will get a square equal to, this is again a plus b whole square. A square plus 2ab plus b square. Here we can write as a 3q whole square is nothing but 9q square. 2ab nothing but 2 3 is 6, 6 2 is 12 cube, and 2 square is 4. Then we can write 9q square plus 12q square plus 4. 4 is the remainder if you take, that is more than the divisor. That's why we can split 4, we can write as 3 plus 1. Therefore 3 of 3q square plus 2, 4q plus 1 plus 1. This is again we take as this total thing as p. Therefore we can write as 3p plus 1. Now we got 3 numbers. These 3 numbers if you square, those are in the form of 3p, 3p plus 1. Therefore in the same way, if you take cube of the number in the form of 9m, 9m plus 1, 9m plus 8, cube of the integer in the form of. But here if you take 9 means you will get 0 to 8. That's why we will take instead of 9, 3 is a factor of 9, we will take as b value is 3. Then you will get these 3 numbers you will get. 3q, 3q plus 1, 3q plus 2. Here also we go with same number cube, but instead of squaring we will take as cubing on both sides. Now each number will cube, that is always in the form of 9m, 9m plus 1, 9m plus 8 we can prove. Here 1 by 4 we can write as 0.25 with the division. Sometimes they can, without doing division, the denominator should be, we need to convert into 2 power n, 5 power m. With balancing, the denominator should be in the powers of tens. And if decimal form is there, we are simply removing the decimal and writing in the form of p by q. And this is both are rational numbers, and some other rational number is non-terminating recurring decimal form. Here we studied already 0.32 bar, that is a repeating, means a non-terminating, bar is there means non-terminating recurring decimal form. Here period we can take as 32 and periodicity is 2. Why? Because here block is 2 digits are repeating, and we can take this period non-terminating recurring decimal form also we can converting into p by q by taking x equal to and multiplying with the periodicity. Already we know how to do this. The next concept is Roti Relations, very important topic, and this is a 4 marks question we can expect. And here there are 3 or 4 methods is there. Here root 2, second one is 2 roots, and third one is rational and irrational combination, and here rational and irrational. Here multiplication, and here the addition or subtraction will be there. And if you go single root 2, I need to prove that, they can ask to prove that root 2 is an irrational number. In this problem we have to go with the contradiction method. Suppose root 2 is a rational number. Root 2 we can write, rational number means we can write in the form of p by q. Here we can express as root 2 as p by q, and q is not equal to 0. P comma q are integers, p comma q are co-primes. We can transpose this q to the left side, we can get root 2 q equal to p. Now squaring on both sides, root 2 q whole square equal to p square. We can apply the formula ab whole power m, nothing but a power m, b power m. We can write here RHS, I am writing as LHS, and LHS we are writing as RHS. Then we can get as p square equal to 2q square. Here p square, these two are the factors of p square. 2 and q square are the factors of p square. We know that factor divides that number, means 2 divide p square. And also we are having one lemma, if p divide a square, then p also divide a. By using this lemma, 2 divide p square means 2 also divide p. And also 2 divide p means 2 is a factor of p. We can express p as 2 into some other number for some k. Now again squaring on both sides, we can get p square equal to 2k whole square is nothing but 4k square. Here p square already we written as 2q square. We can replace in the place of p square as 2q square from equation 1. Then we can get 2q square equal to 4k square. Then here 2 1s are 2 2s are. Now we can write as q square is 2 into k square. This q square again we are having 2 factors. These 2 factors will divide that dividend. 2 divide q square, then plus again we are using the lemma 2. If p divide a square, then p also divide a. 2 divide q square means 2 also divide q. We got 2 divide p and 2 divide q. Since 2 divide p and 2 divide q, 2 is a common factor of p and q. 2 is a common factor of p and q. But by definition of rational number, there is no common factor. P and q, there is only common factor is 1. That's why Here we are getting 2 is a common factor. Why we are getting this one? Because we are assuming wrong. Therefore we can conclude that this contradicts our assumption. Hence root 2 is an irrational number. And the second method, if you go, 2 are the irrational numbers, root 3 minus root 2. We need to prove that that is an irrational number. Suppose same way in the contradiction method we can go, root 3 minus root 2 is a rational number. Again we are applying definition. Root 3 minus root 2 is a rational number, means we can express as p by q, where q is not equal to 0, p comma q are integers and p comma q are co-primes. Now again squaring on both sides, we can root 3 a minus b whole square, here p by q whole square. A square plus b square minus 2ab, that equal to p square by q square. Here square and root will get cancelled, square and root will get cancelled, and here root 3 into root 2 becomes root 6. We can write as 3 plus 2 is 5 minus 2 root 6 equal to p square by q square. And then here minus 2 root 6, we send this 5 to the right side. This is rational part and this is also rational part. We can send it together. Minus 2 root 6 equal to p square by q square minus 5 by 1 we can write. And take the LCM q square, p square minus 5q square. Then this minus 2 also I can transpose to the right side. Then root 6 equal to p square minus 5q square by minus 2q square. From equation 1 we can already prove that single root 2 is an irrational. Then we can conclude this is also root 6 is an irrational part, and RHS is p square minus 5q square by minus 2q square is a rational number. Why? Because since p and q are integers. Therefore rational cannot be equal to irrational. This contradicts our assumption. Hence root 3 minus root 2 is an irrational number. We can conclude that. If you go next method, prove that 5 root 2 is an irrational number. Same way in the contradiction we will go. Suppose 5 plus root 2 is a rational number and 5 plus root 2 equal to p by q. That same definition will apply. Q not equal to 0, p comma q are integers, p comma q are co-primes. Now this is a rational part and this is also rational, and this root 2 is a irrational. We are sending rational part to the other side. We can get root 2 equal to p by q minus 5. Take the LCM, you will get as p minus 5q by q. Here from equation 1, LHS root 2 is an irrational. Already we have proved that. And p minus 5q by q is a rational number since p and q are integers. Here also we can conclude that rational cannot be equal to irrational. This contradicts our assumption. Hence root 2, 5 plus root 2 is an irrational number. Final one is, they can ask here instead of plus they can ask minus or multiplication 5 root 2. This is also very easy method. Here prove that 5 root 2 is an irrational number, means suppose 5 root 2 is a rational number. Same way 5 root 2 equal to p by q, q not equal to 0, p comma q are integers, p comma q are co-primes. Now send 5 to the right side, transposing 5 to the other side. Root 2 equal to p by 5q, that is equation 1. From equation 1 and 2, LHS, here root 2 is an irrational number and RHS p by 5q is a rational number since p and q are integers. Therefore rational cannot be equal to irrational. This contradicts our assumption. Hence 5 root 2 is an irrational number. The next concept is logarithms. Logarithm is nothing but inverse of exponential. We can convert exponential into logarithm, logarithm into exponential. Like this one example, 2 power x equal to 5. Here x equal to, we can, here x 2 is a base and x is a index, or we can say power, and a 5. And we can convert this one into, this is the exponential form, we are converting into logarithm. How means, here base 2 going other side means base 2 only, but adding here log. Exponential changes to logarithm, x equal to log 5 base 2. And here we are having 3 forms. This exponential into logarithm we can convert vice versa. If a logarithmic form is there, we can change into exponential. Exponential is there, we can convert into logarithmic form. But based on these 3 laws, we can find out the logarithmic problems. First of all, first law is log x by base a is nothing but product of 2 numbers, means we can split like this, log x base a plus log y base a. Here also we can use the formula, exponential formulas, a power m into a power n. By using that formulas we can prove these derivations. And log x by y base a is nothing but log x base a minus log y base a. And third law is log x power n base a is n into log x base a. And here one more formula is log 1 to the any base value is always 0, and log a base a is always 1. And they can ask one more questions like this, 2 or 3 times they ask to evaluate log 5 base 25. For this we can use the formula. Let assume this value is equal to x. Log 5 base 25 is x. Then we can say this is in the form of logarithm. We can convert into exponential. How? Here base 25 going other side means base, and this LHS whenever you are removing 5 log, then you will get as 5 equal to 25 power x. This 25 I can write again as 5 square. 5 equal to 5 square whole power x. 5 equal to 5 power 2x. Bases here 5 power is 1. Bases are equate the powers. 1 equal to 2x. Then x equal to 1 by 2. Then finally we can conclude that log 5 base 25 value is 1 by 2. This is the evaluate 1 mark questions they can ask. And if you go, another concept is expanded form and a single logarithmic form. Here this is the question is given single logarithm. We can expand into one term becomes 2 or 3 depend on the factors. Here we can say log 25 by base 32 we can write as 5 square by 2 power 5. This is nothing but log 5 square. This is we here applied as second law. Log 5 square minus log 2 power 5. And again we can use the third law. 2 log 5 minus 5 log 2. Here there are two terms. We can expand a single term into two terms. Sometimes they can give two terms. We need to write single logarithms. In the same process we will go with in reverse order. Again, if you go, next concept is if x square plus y square is 25xy, then prove that 2 log of x plus y is 3 log 3 plus log x plus log y. This is from textbook question. Like this problems 2 marks they can ask. Given this is the condition we take as equation 1, and LHS part if you take 2 log of x plus y is nothing but here we can apply third law. Whenever n into log x means we can write power. Here we can write log x plus y whole square. Here again we can do a plus b whole square, x square plus y square plus 2xy. This x square plus y square already we got equation 1 is 25xy. Replace here instead of x square plus y square we can write as 25xy plus 2xy log 27xy. Again here there are 3 terms we can write as log 27 plus log x plus log y. And here again 27 we can write as 3 cube log 3 cube plus log x plus log y. Again we can write as 3 log 3, third law, 3 log 3 plus log x plus log y, that equal to RHS. Therefore we can solve, this is one method. Other method is from this condition only we can adding or subtracting whatever the process you can, but the best method is you take LHS. But some problems we cannot get from LHS, we have to use this method also, other method also, adding or subtracting 2xy on both sides, and we can check here LHS. If one step, if you simplify log x plus y whole square, in that way we need to follow. And if you go next method is if 2.3 whole power x equal to 0.23 whole power y equal to 1000. This is one more model. Here we need to find out the value of 1 by x minus 1 by y. They can ask 1 by y minus 1 by x, whatever the value they can give, we can find out. Here first 2.3 equate this 2.3 whole power x equal to 1000. We can write 2.3 whole power x equal to 10 cube. We can apply log on both sides. Whenever the powers is there, always you have to apply the logarithms. Here we can apply logarithm on both sides. Then log 2.3 whole power x equal to log 10 cube. Here we can apply the third law. Power, whenever the power is there, we can go for third law. X log 2.3 equal to 3 log 10. Then I want to get 1 by x means you send x to the transpose to the right side and 3 log 10 to the left side. Then we will get as log 2.3 by 3 log 10 equal to 1 by x. Similarly we can get as, if you go with y, 0.23 whole power y equal to 1000, then we can applying log on both sides. If you simplify similarly same process, you will get as log 0.23 by 3 log 10 equal to 1 by y. Now I got 1 by x and 1 by y. We can find out 1 by x minus 1 by y. Here substitute the values log 2.3 by 3 log 10 minus log 0.23 by 3 log 10. Here the LCM is 3 log 10 take, and log 2.3 minus log 0.23. Then here in the numerator, if you observe, that is the second law, we can apply log 2.3 by 0.23 by 3 log 10. Here removing the decimal, and whenever the removing the decimal, you will get numerator removing the decimal, you will get the denominator zeros. If denominator is removing, you will get the numerator zeros. Then we can write log 23 by 23 into, here of decimal after 2 digits we can get numerator 100, here decimal after 1 digit we can get denominator 10. Then 3 log 10. If you simplify, you will get log 10 by 3 log 10. Here, log 10 and log 10 comparing means you can get as 1 by 3. This finishes this problem. And if you go next method is, another model is log x plus y by 3 equal to 1 by 2. log x plus log y, then find x by y plus y by x. In this case, in this situation, this 1 by 2 you are sending to left side, and simplify you will get in the terms of x and y. That make as equation 1 and calculate from here, or you can solve from there only. Then after that, the next model is 2 power x plus y, 2 power x plus 1 equal to 3 power 1 minus x. Solve for x. Whenever the powers is there, I discussed that apply log on both sides and bring x terms to together and constants to the other side. Then you will get x value. In this way, we can finish the real numbers. We can go for next chapter is sets. The next chapter is sets. This is a very small chapter and a very easy concepts. If you go set, what is the definition means? Set is nothing but it is a collection of well-defined objects. Well-defined objects. Here, what is well-defined means there are two conditions. One is common property, and second one it decides that belongs in that set or not. First of all, sets are enclosed with braces, flower braces, and each set we can represent in two forms. One is set builder form, other is roster form. If you go well defined means, here if you take one example, 1, 3, 5, 7 like this, here each element is a common property. What is that? Here everyone is a odd number. Each element is a odd number. 1 is a odd number, 3 is a odd number, 5 is a odd number, 7 like that. Each element is a odd number, and sets are denoted by capital letters. Capital A, capital B, capital C, or X, Y, Z like that. Then if you take here 1, 3, 5, 7, each element have a common property. If you take any even number that does not belong to that set, it decides. These two conditions are satisfied. That's why this collection is well defined. You can select number of examples. You take multiples of 2 or multiples of 10 or perfect cubes or perfect squares, whatever the example you can select. Here you can check the condition. Each element have a common property, and the second thing is whether it belongs to that set or not, deciding factor. Those two conditions satisfying means that collection is a well defined. Hence that becomes a set. If you take second one, roster into set builder and set builder into roster, vice versa, we can convert. Communication standard that comes under. If you take A equal to x such that x is a factor of 20, we can write like this. X such that x is a factors of 20. X is a factors of 20 means here you have to select this is in the form of a set builder. We can take as colon or oblique. Any order we can represent set builder, and we can represent this in the roster form means here we can write for 20 factors, we can write 20 factors is 20 into 1, 4 into 5, 2 into 10. Like this we can write. We can write as 1, 2, 4, 5, 10. Like this, 10 and one more thing, 20 itself. 1 and itself will be always factors of that 20, and remaining all proper factors. We can say that 1, 2, 4, 5, 10, 20. These are factors, and here in the roster form one more condition is each element is separated by commas and thing. Moreover, the element is not repeating. Each element is separated by commas and element is not repeating. And we can convert, if the roster form is there, we can convert into set builder. Set builder is there, we can convert into roster. If you take the roster form 1, 2, 3 like this, we can convert into set builder. How can we write means x such that x is a natural number. That's all. There is no condition. Why? Because if you stop up to 100 means we can write x less than or equal to 100. In this way we can represent. If there and there are types of sets is there. If you go next concept, types of sets. Empty set. Empty set having, we can say there is no element present in that set. Is empty, or we can write as 5. Here we can call as empty set, we call as null set or void set. If you go next, singleton set means if there is only one element present in that set is nothing but singleton set. If there is exactly one element, then we can call that is a singleton set. Equal sets. If you go with here A equal to 1, 2, 3, B equal to 2, 4, 6, these are not equal sets. Why? Because here elements are different. Here 1, 2, 3 is there, here 2, 4, 6. Elements are not same, means every element in A is also an element in B, every element in B is also an element in A, both are equal sets. Therefore those are the definition of equal sets. If you go equivalent set means if you take here A equal to 1 2 3, B equal to 2 4 6. Here number of elements present in the set A is 3, means we can write n of A is 3. If you take number of elements present in the set B is 2 4 6, there are also 3, means n of B equal to 3. We can say that n of A equal to n of B. Then we can say both are equivalent sets. A is not equal to B here. If A equal to B, then we can say that is a equal sets. The difference between equal and equivalent sets is nothing but equivalent means the number of elements should be present same. Means here 1 2 3 is there and 2 4 6. Elements are different, that's why those are not equal sets. If elements also same, we can say both two are equal sets. If you go with the next one is finite and infinite. If you take 1 2 3 1 2 4 5 7, 10 20, this is countable set, means 1 to up to 100 or 1 to 1000, we can ending number is there, we can say that is a countable set, and we can conclude that that is a finite set. If it is a 1 2 3 dash dash means we can say uncountable, and we call those sets are infinite sets. And next concept is subset. If you take this is the set A equal to 1 2 3, we can write how many subsets like this. We can list out first of all empty set is subset to every set. Empty set is always a finite set because that is a countable number of elements present in the empty set is 0. And we can say first thing is subsets. How to represent means 1 2 3 means we can write is 5 is a subset, and single elements, single combinations 1 2 3 1 2 1 3 2 3. And if you take 2 1 means 2 1 we cannot write. Why? Because roster form the repetition is not allowed. Order is you can take any order, but 1 2 2 1 represents same. Whereas in the coordinate geometry, if you take the point 1 2 and 2 1 locates different position, but here in the sets roster form 1 2 or 2 1 both represent the same meaning. Here 5 single element 1, single element 2, single element 3, 1 2 1 3. 2 3 and 1 2 3. Like this, first of all we are writing no empty set, next one element possibilities, next 2 element what are the possibilities, next finally 3 elements. In the same way, if you are having 4 elements, you can go in the same order: single element, 1 element combinations, 2 elements, 3 elements, 4 elements, like that. And one more formula is how many subsets we are existing means we can write this is the formula 2 power 2 cube. Here number of elements is 3, we can take as n value as 3, 2 cube is 8. Therefore we can conclude that there are 8 subsets for this. If these all subsets if you written in one set, then that is nothing but power set. This is topic we are not having in the state board. And if you go union, intersection, difference, 3 more operations. If you take the set A equal to 1 2 3, B equal to 2 4 6. If you take the union operation, union is denoted by like this symbol U, and A union B we can write as 1 2 3 2 4 6. Here what we are doing, union means all the elements should become without repetition. Means if repeating occurring, then we can take only one time. If repetition is occurred, you have to conclude only one time. 1 2 3 4 6. If you take intersection A intersection B, intersection symbol we can write like this, and A intersection B means there is any common elements is there, we need to check. Here 2 and 2 is there, means we can take only common elements. If there are both are disjoint sets, we'll get sometimes. In that case we will write as empty. If there is no common element, we can take as empty. Here we can take as 2 is a common, we are writing single element 2. If some more elements is there, we will take all. Next here the A intersection B is nothing but 2. If you go with A minus B, that is nothing but difference. A minus B means nothing but the meaning is only A, the elements present in only A other than B. Here A is 1 2 3 minus 2 4 6. Here we can write 2 is common is there, not to take this 2 other than only A having as 1 and 3. Therefore we can take as 1 3. If you take B minus A, see subset concept. After that, next if you go union, intersection, difference, we discussed. Union means here we will write the two sets, union between them, and if repetition is allowed, we won't take, only one time. All the elements should become and without repetition. One time only we are taking. And if intersection operation, we are taking only common element. If there is no common element, we will take as empty set. Or here 2 is a common, we will take as 2. A minus B, here 1 2 3 2 4 6. Here any common elements is there, A and B, then remove that common element and only A contains elements will list out here. 1, 3. Here only A is 1, 3. If you take B minus A 2, 4, 6, 1, 2, 3, B minus A is 4, 6, we can take as B minus A means nothing but here only B, not in A elements. That's why we will remove 2, we will write as 4, 6. If you take, and this is the Venn diagrams, if you take A union B means total, and if you take A intersection B means only this region will get a common portion, and if you take A minus B means only this part, only A which is not in B, and if you take B minus A means only in B which is not in A, this region. That's why we can say by Venn diagram we can say union, intersection, difference of sets, we can get easily understandable. And if you go with the last concept is, if you take verify n of A union B is n of A plus n of B minus n of A intersection B. If whenever the sets are disjoint, we can say that both are no common elements. Here in this case n of A intersection B is empty, n of A intersection B empty means we can say those are the number of elements present in that set is 0. We won't get this case if both are disjoint. And then after that we can list out here A is 1, 2, 3, the number of elements, coordinate of a set is 3, n B equal to 2, 4, 6, we can write n of B is 3, and number of elements present in B is 3, A intersection B 1, 2, 3, intersection 2, 4, 6, A intersection B is 2, then implies n of A intersection B is 1, number of elements present in that set is 1, A union B is 1, 2, 3, union 2, 4, 6, A union B is 1, 2, 3, 4, 6, number of elements present in that set is 5. Next, if you take LHS part n of A union B, we got 5. RHS, if you take n of A plus n of B minus n of A intersection B, 3 plus 3 minus 1, that is nothing but 6 minus 1, that equal to 5. We got LHS and RHS are 5, 5, therefore we can conclude that n of A union B equal to n of A plus n of B minus n of A intersection B. Finally, sometimes we can represent the set like this, subset. If you take subset, A is 1, 2, 3, B value is 1, 2, 3, 4. Then we can write A is subset to B. We can represent like this also, Venn diagrams. A is 1, 2, 3, B is 4. Sets are generally represented with Venn diagrams are generally represented with rectangular boxes, and mu is a universal set. We can represent like this also, Venn diagrams. Thank you. This completes sets.